Right now, somewhere in your house, there's probably a candle. Maybe it's decorative, sitting on a shelf. Maybe it's in a drawer for emergencies. You think you understand what it is, a simple object. Wax, a wick, something that burns and gives light. But what if I told you that a burning candle is one of the most profound and mysterious phenomena in the entire universe? That packed into that tiny flame is nearly every major principle of physics and chemistry? That understanding a candle means understanding the sun, the origins of life, and the fate of the cosmos? I'm Richard Feynman, and I once gave a series of lectures on the chemical history of a candle, following in the footsteps of the great Michael Faraday. And what I discovered, what Faraday discovered, is that a candle is not simple. It's a portal into understanding everything. By the time we're done, you'll never look at a candle the same way again. You'll see in that small flame the secrets of thermodynamics, quantum mechanics, chemistry, fluid dynamics, and even the origin of your own existence. Let's light a candle and watch closely. The mystery is about to unfold. Look at a candle flame. What do you see? You see light. You see colors, yellow, orange, maybe some blue at the base. You see the flame flickering, dancing, responding to air currents. You might see smoke rising. Simple, right? You light the wick, the wax melts, the wick burns, you get light and heat. But let me ask you some questions that will reveal how little we actually understand about this everyday object. Why is the flame shaped like a teardrop? Why is it hollow in the middle? Where exactly is the wax going? Why are there different colors in different parts of the flame? What is actually burning, the wick or the wax? Why does the flame flicker? Why does blowing on it make it go out, but blowing harder on coals makes them hotter? If you can't answer all of these questions precisely, then you don't really understand what's happening in a candle. And that's okay, because answering them will take us on a journey through nearly every branch of science. Let's start with the wax itself, because even before we light the candle, we're already dealing with something remarkable. Candle wax is typically paraffin, a mixture of hydrocarbon molecules, usually with between 20 and 40 carbon atoms in long chains. The chemical formula is roughly CH, though it varies. But here's what's fascinating. Where did these hydrocarbons come from? Most candle wax comes from petroleum, which formed from ancient organic matter, plants and tiny organisms that lived hundreds of millions of years ago. These organisms captured energy from sunlight through photosynthesis, converting carbon dioxide and water into sugars and starches, energy-rich hydrocarbon compounds. When these organisms died and were buried under layers of sediment, subjected to heat and pressure over millions of years, their complex organic molecules broke down into simpler hydrocarbons, oil and natural gas. So when you light a candle, you're releasing energy that was captured from sunlight by plants that lived during the Carboniferous period, 300 million years ago. The candle is a chemical time capsule. The energy in that flame is ancient sunlight, stored for hundreds of millions of years in chemical bonds, now being released in your living room. But it gets even more interesting. Those hydrogen atoms in the wax, they were formed in the Big Bang about 13.8 billion years ago. The carbon atoms, they were forged in the cores of massive stars that exploded as supernovae billions of years ago, seeding the galaxy with heavy elements. A candle is made of stardust, powered by ancient sunlight, demonstrating principles that govern the cosmos. Now let's light the candle and watch what happens. This is where the mystery deepens. When you first apply heat to the wick, from a match or a lighter, the wax near the wick melts. The liquid wax is drawn up the wick by capillary action, the same force that allows trees to pull water from their roots to their leaves. As the liquid wax reaches the hot part of the wick, it vaporizes. It turns from liquid to gas. And here's the critical point. The wax vapor is what actually burns, not the solid wax and not the wick itself. The wick is just a delivery system, a capillary tube that brings liquid wax to the heat zone where it can vaporize. If you look closely at a candle flame, you'll see the wick isn't being consumed very quickly. It's the vapor around the wick that's burning. When the wax vapor mixes with oxygen in the air and reaches the ignition temperature, combustion occurs. The hydrocarbon molecules react with oxygen, CH plus OCO plus HO plus energy. But this isn't happening all at once. It's happening in zones, in layers, creating the structure of the flame. And here's what's remarkable. The flame is self-regulating. It creates exactly the conditions needed to sustain itself. The heat from combustion melts more wax, which gets drawn up the wick, which vaporizes, which burns, which creates more heat. It's a perfect feedback loop, a self-sustaining chemical reactor that requires no external input once started. This is the same principle that powers all combustion engines, all fires, all stars. The candle flame is a miniature model of stellar fusion, different chemistry, same principle of self-sustaining energy release. Now let's look at the flame more carefully, because its structure reveals beautiful physics. A candle flame has distinct zones, each with different chemistry and different temperatures. The dark zone enter, near the wick. This is where wax vapor is rising but hasn't yet mixed with enough oxygen to burn. It's actually relatively cool, around 600 C. If you carefully insert a thin tube into this zone, you can draw off wax vapor without burning it. You could lead this vapor away and ignite it elsewhere, proving that the dark zone contains unburned fuel. The luminous zone, right Lorentz, this is where partial combustion occurs. There's not enough oxygen for complete combustion, so instead of all the carbon combining with oxygen to form CO, some of it forms tiny solid particles, soot. These carbon particles are heated to around 1000 C, and hot enough to glow, they emit blackbody radiation. Here's something beautiful. The yellow color you see isn't a property of fire itself. It's the thermal radiation of hot carbon particles. If you burned pure hydrogen and oxygen, the flame would be nearly invisible because there's no carbon to create glowing soot. The color tells you the temperature. Using Wien's law, we can calculate that yellow-orange light with a wavelength around 600 nanometers corresponds to a temperature around 1000 C. Exactly what we measure. The blue zone, this is where complete combustion occurs. There's plenty of oxygen here, and the chemistry is different. You're seeing chemiluminescence, light emitted directly from the chemical reaction, not from hot particles. The blue comes from excited CH and C radicals, molecular fragments created during combustion that emit blue light as they decay to lower energy states. This is quantum mechanics in action. The chemical reaction pumps these molecules into excited quantum states, and as electrons fall back to lower energy levels, they emit photons with specific wavelengths, the blue light you see. The invisible zone, beyond the visible flame, is a zone of hot gases, mostly CO and HO vapor, the products of combustion. This region can extend several centimeters beyond the visible flame. The flame is not a thing, it's a process, a dynamic structure maintained by continuous flow of matter and energy. Why is a candle flame shaped like a teardrop? This question takes us into fluid dynamics. The flame heats the air around it. Hot air is less dense than cold air, so it rises, buoyancy. This creates a convection current. Cool air flows in from the sides, gets heated by the flame, and rises, carrying combustion products with it. This flow shapes the flame. The rising hot gases stretch the flame upward. The inflowing cool air from the sides squeezes it inward at the base. The result is the characteristic teardrop shape. But here's something remarkable. In zero gravity, candle flames are spherical. Astronauts have burned candles on the International Space Station Without gravity, there's no buoyancy, no up for hot air to rise toward. The flame becomes a perfect sphere, with cool air diffusing inward and hot gases diffusing outward in all directions. This spherical flame is less efficient. It gets less oxygen supply because there's no convection to bring fresh air. It's also dimmer and burns more slowly. The shape of a flame on Earth is determined by gravity, one of the fundamental forces of the universe, visible in your living room. The flickering you see is turbulence in the airflow. Tiny variations in air current create instabilities in the convection pattern, causing the flame to dance. It's the same fluid dynamics that creates turbulence in rivers, in the atmosphere, in the flow of blood through your arteries. Let's talk about the light itself, because this is where things get really deep. As I mentioned, the yellow-orange glow comes from hot soot particles. But why does hot matter glow at all? This question led to one of the most important discoveries in physics. In the late 1800s, physicists were trying to understand blackbody radiation, the light emitted by hot objects. Classical physics predicted that hot objects should emit infinite energy at high frequencies, the ultraviolet catastrophe. Obviously, this didn't happen. Hot objects don't emit infinite energy. Something was wrong with the theory. In 1900, Max Planck solved the problem by making a radical assumption. Energy is not continuous. It comes in discrete packets, quanta. Light, Planck proposed, is emitted in chunks of energy proportional to frequency, E tug UH, where is Planck's constant, and F is frequency. This was the birth of quantum mechanics, and it was motivated by trying to understand why hot objects, like the soot in a candle flame, emit the spectrum of light they do. Every time you look at a candle flame, you're seeing quantum mechanics in action. The blackbody radiation from those glowing carbon particles follows Planck's law. The color distribution, the spectrum, is determined by quantum principles. And the blue light at the base? That's also quantum mechanics. Chemical bonds are quantum mechanical entities. When molecules react, electrons transition between quantum states, and these transitions emit photons with specific quantized energies. The flame is a classroom demonstration of quantum theory, happening spontaneously in your home. Here's a question that puzzled people for centuries. Where does the wax go? You start with a solid candle. You burn it for hours. The candle gets shorter. Where did the wax go? It didn't fall off. It didn't leave a residue. It just disappeared. Before modern chemistry, this was a deep mystery. Some thought the wax was consumed by fire, whatever that meant. Some thought it turned into phlogiston, a hypothetical substance released during burning. The truth is more beautiful. The wax doesn't disappear. It transforms. Matter is conserved. It just changes form. When you burn a candle, the wax, those long hydrocarbon chains, reacts with oxygen from the air. The carbon atoms combine with oxygen to form carbon dioxide, which is a gas that disperses into the air. The hydrogen atoms combine with oxygen to form water vapor, also a gas. If you put a cold glass surface above a candle flame, water condenses on it. You can see the water droplets. That water was created by the flame, formed from hydrogen atoms that were in the wax. The wax became gas. Solid became invisible. But the atoms are all still there, just rearranged, bonded differently, dispersed into the atmosphere. Here's something mind-blowing. When you burn a candle, you're getting heavier. Wait, what? Yes. Every breath you take contains some of the CO from candles, from fires, from combustion all over the world. Your body extracts oxygen from the air you breathe. Meanwhile, the food you eat contains carbon and hydrogen. Through metabolism, you're doing the same chemistry as a candle, combining hydrocarbons with oxygen to release energy, producing CO and HO. You are a slow, burning candle. The chemistry is identical, you're just doing it in a controlled way, at a lower temperature. using enzymes to manage the reactions. The calories in your food are measured by literally burning the food and measuring the heat released, the same energy your body will extract through metabolism. A burning candle demonstrates the second law of thermodynamics beautifully. Before burning, you have organized energy stored in chemical bonds, low entropy, high free energy. You have a structured object, the candle. After burning, you have dispersed heat energy spread throughout the room, high entropy, low free energy. You have dissociated molecules, CO and HO, randomly mixed into the atmosphere. The candle demonstrates the arrow of time, the tendency of the universe to move from order to disorder, from low entropy to high entropy. You can burn a candle and disperse its energy, but you cannot gather that dispersed heat, that CO, that HO vapor, and spontaneously reassemble a candle. The process is irreversible. This is true of everything. You age, buildings decay, stars burn out. The universe moves inexorably toward heat death, maximum entropy, uniform temperature, no free energy, no structure. The candle's life is a microcosm of the universe's life. It burns bright, creates order and light and warmth, and then fades into cold disorder. But there's beauty in this. The temporary island of order, the flame, is made possible only by increasing disorder elsewhere. The candle creates local order, the structured, by exporting entropy and dispersed sh. This is what all life does. You maintain your ordered structure only by consuming low entropy energy sh, and expelling high entropy waste sh, CO, other waste products. A candle flame is alive in a sense. It's a dissipative structure, a persistent pattern maintained by throughput of matter and energy, just like you. Let me bring all of this together and tell you why candles are truly mysterious. A candle is simple materials, hydrocarbons and oxygen, yet from this simplicity emerges extraordinary complexity, self-organization, multiple zones of different chemistry, quantum light emission, fluid dynamic patterns, irreversible thermodynamic processes. The candle demonstrates that complexity emerges from simplicity when you have the right conditions, energy flow, chemical reactions, feedback loops. This is the same principle that led to the origin of life. Early Earth had simple molecules, water, CO, methane, ammonia. Energy from lightning, volcanic heat, and sunlight drove chemical reactions. Eventually, self-sustaining chemical systems emerged, systems that could maintain themselves, reproduce, evolve. The candle flame is a non-living analog of life. It's self-sustaining. It responds to its environment. It has metabolism. It maintains a structure despite constant turnover of material. It eventually dies when fuel runs out. Michael Faraday, who gave the original lectures on the chemical history of a candle in 1848, understood this. He said, "There is no better. There is no more open door by which you can enter into the study of natural philosophy than by considering the physical phenomena of a candle. Everything you need to understand about the universe is in a candle. Atomic structure, the carbon and hydrogen that make up the wax. Chemical bonds, the energy stored and released. States of matter, solid wax melts to liquid, vaporizes to gas. Thermodynamics, energy transformation, entropy, irreversibility, quantum mechanics, blackbody radiation, chemiluminescence, fluid dynamics, convection, turbulence, flame shape, gravity, the buoyancy that shapes the flame. Conservation laws, mass and energy are conserved, only transformed. Stellar nucleosynthesis, the carbon was made in, stars. The arrow of time, the irreversible increase in entropy. The candle contains the universe in miniature. So why are candles the most mysterious object in your house? Not because they're strange or inexplicable. Quite the opposite. They're mysterious because they're so rich with meaning, so dense with scientific principles, so profound in their simplicity. A candle is mysterious because understanding it completely means understanding almost everything. When you understand a candle, you understand where matter comes from, decosynthesis, where energy comes from, photosynthesis, how chemical reactions work, why hot things glow, how quantum mechanics determines light emission, why gravity matters to fluid flow, why time has a direction, what life is in essence a self-sustaining pattern of chemical reactions. The next time you light a candle, for ambiance, for celebration, for comfort, take a moment to really look at it. See the ancient sunlight being released. See the stardust burning. See the quantum transitions creating colored light. See the self-organizing system maintaining itself. See the arrow of time playing out in real time. See the universe in a flame. That's what Faraday saw. That's what I saw. That's what you can see if you look closely enough. The candle is not simple. It never was. It's a gateway to understanding everything: chemistry, physics, the origin of life, the fate of the cosmos. And it's sitting in your house right now, waiting for you to really see it. Thank you. Now go light a candle and watch the universe unfold in that tiny flame. The mystery isn't that we don't understand it. The mystery is that such profound truths can be so beautifully packaged in something so small and ordinary. That's the real mystery. And that's the real magic.